what I have been doing this whole summer is working with a existing search engine algorithm called LADR, LADR, and it stands for Lexical Accelerated Dense Retrieval. I think we need to start by talk about what is a lexical retrieval, right? So by doing a lexical retrieval, you query, typo here. For example, your query is apple, right? And then you'll get results like apple tree, apple juice, apple computer, etc. But so whatever algorithm that you're using, if it's a lexical retrieval method, mainly what it does is that it will retrieve the most relevant documents that contains the exact term. Of course, there are variations to this type of stuff, like you can do a document expansion or query expansion. Say you try to guess like what document is missing from the document and try to add that before you do any search, like you try to add that in indexing time. Or you can expand the query to try to add related terms in the query so that it does a better search in terms of lexical retrieval, right? But there's a problem that it doesn't really talk about the meaning of the document or the query of some terms. For example, you have the band, the who, right? The who is a term not that very frequent, but it appears from time to time. But for the method, the and who are two very insignificant terms because they don't really have a meaning. Not like apple or like juice. It's more like the what here, right? It doesn't really matter. But in terms of the who is important, and that's the type of stuff that lexical retrieve has problem with. So we have what's called dense retrieval. It's dense because the vectors that we convert documents into, they are dense in terms of there's not many ones and zeros. Just to how to explain this? So essentially, dense retrieval is that you try to capture what's called the semantic meaning of the query and the document, and then you convert that into a vector. We do this with language models. The problem with dense retrieval is that it's not any good, but the better the dense retrieval the method you use means it's always more expensive, right? Because you need more accurate result, meaning you need more GPU, CPU time for the language model to process this kind of stuff. And so, for example, if you put query the who, it might be the one that actually tells you about is English rock band instead of some dictionary, right? So that's the idea. It captures the semantic meaning, like it's trying to say essentially. It's more like it's somehow like ChatGPT stuff, So it's smarter, but it's slower, and we know that a search engine is something that we need to access maybe millions of times per minute, so it needs fast. So LADR is one of those methods that tries to achieve a dense retrieval performance and makes it more efficient. Right, so how does it make more efficient? As the title said, it does a lexically accelerated dense retrieval. What does that even mean? Alright, so essentially what it does is a two-stage retrieval, right? It's a two-stage retrieval. So in the first stage, it quickly maybe get 1,000 results. Or 10,000, I don't know, but it's usually not that much. And in the second stage, what it does is that it uses dense retrieval method among those 1,000 results rather than the millions of billions of documents that you need to run through a database for a search engine company. So it then just dense retrieval among the top 10,000 results, and ideally this will give us just as good as results as using an expensive, top performance dense retrieval method like what we call SPLAY. Well, so SPLAY is the state of the art in terms of retrieval accuracy and stuff. But what LADR does is it's quick, and especially with so if you give it very little time, its performance accuracy is very solid. Okay, so what's the algorithm exactly? That goes to here. So yes, so this is what LADR does with a quick look. There's two kinds. The first kind is called the proactive LADR. Essentially, when Q comes in here, it actually retrieves R0, the initial seeders, maybe 1,000 initial seeders, and then it finds the neighbors. By neighbors, I mean vectors that are similar to those initial seeders. And those neighbors are pre-computed. That you know whose neighbor is who, so there's almost no time wasted in this stage. And maybe you find every 32 seeders, every 64, every 16 is your choices. And then you find those seeders. Why do you need those neighbors exactly? It's because lexical retrievers, they're not that good, and we're worried that they might miss some important passages. But, well, it's not that bad either, right? So what it retrieves, if it's not exactly what we want, it at least is close to what we want in terms of a vector. So we can search for the vectors that looks like what we have as initial seeders, and our assumption is that, okay, we'll find what we want among those neighbors. And then when we have those neighbors, we have the final seeders, which is called R1. We feed R1 into a dense score. That is what we use when I talk about that is expensive but captures semantic meaning. This is pretty expensive, but if you only do that to 10,000 packages, it's not that bad. And what a dense score does in this stage, it re-rank what you have from R1. So there's a ranking in R1 from, say you have 10,000 results, you rank them from the first one to the last one, and then you re-rank those, and then you can choose, maybe you only want top 1,000 results, maybe top 100, but essentially we're counting on that this re-ranker will help us to find, to put the top results in top places. Okay, and for active LADR, it does something a bit different, but essentially the idea is the same. So say you have a dense, so you have initial seeder at R0, right? But then you have a dense score in the first place. Why? Because then you go into a loop where whatever you have at the stage as the seeder, you re-rank it, and you'll only find neighbors for the top results, top C results, not for all of the initial seeders. And then you add those neighbors into your seeders, and so now you have the opportunity to find neighbors of the neighbors if that neighbors is ranked pretty high by the dense score. So active LADR is usually considered better, but there's a problem that it might converge until it fully search every piece of document in our corpus graph, which is our whole database. That doesn't really happen, but yeah, so essentially, it gives the retriever the ability to solve shifts to the real important or real relevant documents if our initial retriever doesn't really get to that in the first place. Okay, so this is the algorithm, but I don't think anyone need to look at it. For the proactive LADR, this is for the active LADR. So yes, computation for the active LADR is a bit different. So that is just the number of seeders times the neighbors. But for this one, you have D. D is every single document in the corpus graph. It's dangerous, but it's not that really dangerous. We will do that in practice. And LADR is comparing to those following methods. But I don't need to bore you with this kind of stuff. Instead, I think I should get to the point. This is a quick graph to show you what LADR can achieve and can't achieve. So essentially, it's a very strong method at very low latency. This also sort of says that, okay, it's a very strong method. Okay, so one limitation of LADR is that its operational points with a low time budget does not exist. It's the nature of LADR, and it's not really my topic. So I will introduce to you what I've been doing very quickly. So essentially, what I've been doing is to discuss the impact of initial seeders on the end-to-end performance of LADR structure. Essentially, what I do is I do experiments for different structures. So LADR, as we can see, it has initial seeder, R0, and how this is computed is that we use something in BM25 in the original paper. This is a very popular algorithm, but there's also some a bit more expensive but better performing retrieval method for this first stage retrieval for initial seeders. And so this is one part of my work, which is to investigating how initial seeders changes the ultimate performance of LADR. And so this is still an ongoing work as I mentioned, but I did try something in terms of, so I use Spade C. Spade C dramatically increases the performance of LADR, but Spade is considered the state of art, and one of the most expensive dense retrieval method. We also use some other method called deep impact. This is my focus. Essentially, I use deep impact to try to investigate its impact on the end-to-end performance of LADR, and I try to do a document expansion and see how does that impact LADR. So in terms of trying different first stage and analyzing their effect on the end-to-end performance of LADR retrieval, is that LADR retrieval is very robust, that it doesn't really care if you're using a slightly better or slightly worse or a much better seed, except for state. But state itself is performing so good. Yes, and so on another part is that, which is what I'm currently doing, is that I try to compare the effect of a pure two-stage retrieval without LADR. How does that work? So how does the explored labor structure actually work if I just use a depth score? Like if I just use a depth score without this step, how would that look like? That's some ongoing work, but so far what I got is that LADR is pretty important for worse quality seeds, and I managed to use a very stupid but I consider very effective way to create bad seeds, which is I sort of randomly choose seeds from R0, so and re-rank those. Maybe say I have like 1,000 seeds from R0, but I only use 100 of them. I don't use the top 100 results. I use maybe, since it's random, I don't really know what I use, but I use worse results, but definitely not the top 100 or top 200 results and feed it to LADR. LADR seems doing pretty good with this, as long as it has 30% to 50% of actually good seed in it. Yes.